Welcome, everyone, to the 144th meeting of Introductions in Group Theory and Private Categories. Our speaker today is Jack Davis from the University of Wuppertal, and he'll be talking to us about ambidextrous global spectra and tempered cohomology.
Okay. Can everyone hear me okay?
Yeah.
Okay, perfect. Then, yes, well, thank you for the invitation, Rudradeep, and thanks for everyone for coming. So you can see the title of my talk right here, and it's the same title as a recent paper of mine with William Balderrama and Sil Linskens. And I'm not going to assume that you have any familiarity with any of these words in the title. So maybe let me just say a few words about that. Roughly what we do in this paper are three things. The first one is we define what this first line is. So we discuss these ambidextrous global spectra, which are supposed to be a generalization of a collection of equivariant spectra for every group G that are somehow very compatible, but which have even more structure than Schwede's global homotopy theory, meaning that they have not just transfers for injections of finite groups, but also for surjections or arbitrary pi-finite morphisms. So the first thing we do in that paper is we define this category of ambidextrous global spectra. And then the second thing we do is we give these tempered cohomology theories as an example, because of course there's not much point having this fancy category with fancy objects if we don't know any examples of these objects. So we use these tempered cohomology theories, which are some really nice cohomology theories defined by Lurie in elliptic cohomology 3. They're essentially generalizations of complex K theory. So they all have a T-equal completion theorems and character theories. They're all very well behaved. And most of the work in the paper goes into proving that these tempered cohomology theories of Lurie actually are examples of these ambidextrous global spectra. And then the third thing that we do in this paper is we essentially just explore some properties of everything. So we say, okay, we understand these tempered cohomology theories now as global spectra. So what can we say about these equivariant objects? What can we say about their homology or their geometric fixed points, or, well, and maybe I'll only get that far today. So that's roughly the outline of the talk too, is I'm going to start by giving some motivation to what these ambidextrous global spectra are. I'll really start from the beginning. Then I want to reintroduce these tempered cohomology theories of Lurie, and I'll give K theory as an example, and another example you should keep in the back of your mind, and is a lot of motivation for me and Sil and William, is equivariant elliptic cohomology. Then in the third part, I want to talk about the main theorems of this paper. So, well, how you can combine these previous two sections and view tempered cohomology theories as ambidextrous global spectra. And then in the fourth part, I want to sort of talk about applications. So things like, well, like I already said, the homology, the geometric fixed points of tempered cohomology theories, which up to now sort of were a little bit difficult to analyze. Okay. Feel free to post questions in chat. I've got my computer right in front of me, or just raise your hand, say something out loud. I'll try to respond. But otherwise, let's get started. So yes, let's start with some motivation. So the key observation, or the key observation that gets global homotopy theory started is that a lot of G-equivariant spectra, things like G-equivariant complex K theory, real K theory, complex Bordism, and the sphere and stuff like this, they're all defined uniformly for all groups at once. So this has been observed for many, many years since Attia Siegel were discussing these things. Greenlees May did a lot of work on this, but it was all put together in Schwede's book called Global Homotopy Theory, where he defines some rigorous homotopical foundations for what it means to have a collection of spectra for all groups simultaneously, which somehow have some kind of compatibility between each other. And one way to phrase this in modern language and in a way that'll help with the discussion to its generalization is as follows. So you start with a subcategory of spaces. Let me use this. Start with a subcategory of spaces called the global indexing category. And this is the subcategory of the infinity category of spaces spanned by those spaces of the form BG, where G is some finite abelian group. There's also variants of this where you don't think about abelian groups, but for our applications for tempered cohomology, it's useful to have abelian there. Okay, so you have this category of global spaces, and this is kind of how we're going to parameterize these global spectra, or it's going to roughly be like a functor from GLOAB, although it's going to be refined a little bit. So then you define the category of global spaces, which is just a presheaf category on this global indexing category. So you might have already seen this category of global spaces in another name. It's also very closely related to this category of Orbi spaces. Okay, so now you can define a global cohomology theory, which is sort of the global version of what an equivariant cohomology theory should be. So a global cohomology theory is just a functor from this category of global spaces, so it's this presheaf category, into spectra, which preserves limits. So it sends colimits of global spaces to limits of spectra. This is just a verbatim generalization of what you would call classical homology theory. It sends colimits of spaces to limits of spectra. Sending your cofiber sequences to fibers in spectra, giving you Maéville torus long exact sequences, all these sorts of things. Okay, so this is a global cohomology theory where it's the beginning, the sort of simplest type of stable global homotopical object that we're going to look at. And let me just comment for a moment how you can turn a global cohomology theory into an equivariant cohomology theory. And the way to do that is as follows. So if you have some G space X, then you can construct an Orbi space from this, or I should be consistent. I should call this a global space. So you can construct a global space out of this G space, which is this orbifold quotient, this global quotient, stacky quotient, whatever you want to call it. And you can really write down a formula for it. So, I mean, this is defined as some object in this category of presheaves, and you can define its value on some BH by this formula here. Yeah, notice that in particular, it sends, this functor is sending this free G space, this G on G coset, the point, to a point mod G, which is the orbifold model for BG. So that's a useful example to keep in mind. So this functor, which sends a G space to this orbifold quotient, to this global space quotient, gives you a functor like this from G spaces to global spaces. And if you post-compose this functor with a global cohomology theory, you end up with a G-equivariant cohomology theory. So in this sense, you can see that once you have a global cohomology theory, you get a collection of G-equivariant cohomology theories for every finite group G. Okay. So one comment to make at the moment is that these global cohomology theories are all naive in the sense that there are no transfers involved. They're just cohomology theories. You don't have any Brown representability equivariantly until you ask for transfers. So this brings us to the definition of a global spectrum. So a global spectrum is exactly the same type of data. It's a functor, this time not from this presheaf category into spectra, but now from some span category. So it's well, let me just read it. So a global spectrum is a functor from this span category into spectra, whose restriction to global spaces is a global cohomology theory. So essentially all you've done is you've said, well, let me just remind us what a span is. So remember that, do I have space down the bottom? Yeah. Recall that the objects of this span category are just the objects of this category of global spaces, but that the morphisms in this span category are, they're not just morphisms from X to Y, but they are spans like this, where you allow any map to sit in the left-hand variable here, and these right-hand maps you force to be in this category R. So this lies in R, where this category R is just those maps of global spaces that are induced by injections of finite abelian groups. Okay, so what's the difference between a global spectrum and a global cohomology theory? Well, you don't just have the functoriality in restrictions against all maps of global spaces, but you also have backwards maps induced by these pi1, these injections on pi1. So in particular, these forward maps are giving you transfers. So for every inclusion of finite groups like this, it gives you a map like this in the category of global spaces, which is an injection on pi1, and the associated map now going in the forward direction associated to this global spectrum is encoding exactly this transfer. Okay. I feel like I've said a lot of information. I've shouted a lot of information at the screen already. Um, One other thing I want to remind you of is that remember that to compose spans, so if you have two spans like this and W prime, you take the pullback. So you take a pullback here, you get something P, and then you get a span defined by taking these two compositions. And the nice thing about using this span category and phrasing a global spectrum in this way is that it encodes a lot of information, like the fact that transfers are satisfy Frobenius reciprocity, or the fact that when you compose a transfer with a restriction, you can try to compute that by doing with some sort of Mackey formula, which is given by computing what this pullback is. Okay. Okay. So for us, that's going to be the definition of the category of global spectra. It's going to be this span category, this category of functors from the span category, which restricts to global cohomology theories. Okay. Are there any questions so far? Okay. Then I'll continue. So the first observation that we make in this paper is that this definition is very flexible. Like, I hope that when you saw this first picture, you were maybe a little bit distracted by the fact that the maps that we allow in the covariant variable are just something that we chose. Like, they're just something that we chose to define what a global spectrum is, but you could obviously change what this right-hand variable is and get a variant of a global spectrum. And that's just exactly what ambidextrous global spectrum is. So our first observation is just if you fix some subcategory of this category of global spaces, then you can define what a Q ambidextrous global spectrum is in exactly the same way that I just defined a global spectrum. It's just a functor from a span category where I now allow my right-hand maps, my covariant maps, to lie in this potentially bigger, potentially smaller, potentially unrelated subcategory Q here. Such functors from this span category into spectra whose restriction along to the left-hand maps in the contravariant variable is a global cohomology theory. The thing that I like about this definition is that it's very simple. I mean, some definitions that are complicated are also lovely in their own way, but this definition is very straightforward and it makes it very clear the difference between a Q ambidextrous global spectrum and the previous definition of a global spectrum. Okay, and so we're going to write global spectra with a sub Q to denote this category of Q ambidextrous global spectra. Um, just a note, I set up here that this category needs to be replete. I mean, that's just some random adjective that we need so that this span category makes sense, and so that a lot of properties that you want to prove about this category here make sense. You can look it up in the paper. It's not super important what it is. Okay, so let's see some examples of this. Let me hold it here. So for example, if you take Q to be something rather tautological, you take it to be only isomorphisms, then your definition of a Q ambidextrous global spectrum isn't anything more than just a global cohomology theory, because all of your transfer maps are just isomorphisms. So you could take them to just be the inverse of the associated contravariant map. So in this sense, the definition of a Q ambidextrous global spectrum in this trivial case recovers just a global cohomology theory. In a more interesting direction, so in a non-trivial direction, you could take Q to be generated by not just the injections in this global indexing category, so not just induced by pi1 injections, but induced by any maps in the global indexing category. So you have maps from BG to BK, which are not just injective on pi1, but they could be anything. And this gives you a category that's strictly more structured, that's strictly a generalization of the category of global spectra, which now has transfer maps along any group homomorphism. And this idea is not without precedence. So the idea that there can be equivariant cohomology theories which have transfers against not just injections, but also surjections or arbitrary maps of groups is something that's been observed before. For example, you can write down just by hand these sorts of transfers along surjections or deflations, as they're often known, for K-theory just by hand. So here's what it does on pi 0, for example. The deflation on this representation ring is just sending a representation to the base change of the representation along the complex group ring. Okay, so this is nice. I've got a question. Let me go to it. Is there a reason you use global spaces and not just Mackey functors defined on GLO? Yes, you want to use, we want to use GLO-AB to set things up, which is really, it's sort of abelian groups play an important role there. Whereas if you use the whole global spaces, you can now talk about transfer maps between not necessarily injective maps between not necessarily abelian groups. So that really helps in the setup. Yeah, I hope that answers your question. Okay, so one generalization, or a particular Q, sorry, that we'll be interested in this talk, and a Q that plays a really important role in our paper, is when you take Q to be the collection of all maps of global spaces such that they are relatively pi finite. So this means that for all maps from an element of GLO into your codomain, the pullback is some global space, and you ask that is in the image of a certain right adjoint from spaces, and that this has finitely many homotopy groups concentrated in finitely many dimensions. So think of maps between Eilenberg-MacLane spaces, maps between generalized Eilenberg-MacLane spaces, maps between sort of spaces with finitely many homotopy groups concentrated in some finite interval or something like this. In other words, it's a big generalization of any maps between from BG to BK for any map induced by any maps of groups, any group homomorphisms. I'd hate to see that sentence transcribed. Okay. So this gives us a category which I want to call GLO sub pi, which is called, or the category of pi ambidextrous global spectra. Okay. So the reason why we're interested in these pi ambidextrous global spectra is because it is the biggest subcategory. This particular Q is the biggest subcategory that we're interested in, for which we can produce interesting examples. Okay. So if you look in section 2 of our paper, we prove a lot of basic things about this category of Q ambidextrous global spectra, like its stability, presentability, symmetric monoidality, and all this sort of stuff. So if you're interested in these sorts of things, I'll push you in that direction. What I'm more interested in is trying to produce some examples of global spaces some examples of these ambidextrous global spectra. And for that, we're going to jump into tempered cohomology theories. So I usually start my tempered cohomology motivation with the following example, which is a computation in complex K theory. So if you want to compute pi zero of the equivariant K theory for the cyclic group Cn, well, this is just this representation ring Cn. And this representation ring has a really explicit formula. You can write it in terms of this quotient here, well, L is a tautological line, the tautological one-dimensional representation that you've pulled back from U1. Okay, so this is all a computation that you could just sit down and do. And here is the observation. It's that this is the same as the global sections of the N torsion of the multiplicative group scheme. So this is the N torsion, and this is the multiplicative group scheme. Okay. So what happens when you can, this is a very algebraic statement. I can turn it into a geometric statement by taking spec. So this gives me something like spec pi 0 Cn of Ku is the same as Gm, well, the N torsion of Gm. And another way to write that down in a way that more clearly depends on the cyclic group is to write this as a homomorphism scheme from the cyclic group into Gm. And now I'm going to do something which maybe seems a little confusing. I also want to take a Pontryagin dual here. I'll justify that Pontryagin duality. You can justify that Pontryagin duality yourself by considering the variance of this left-hand side in Cn. It sort of forces you to have some sort of duality on the right-hand side for this to make sense. Anyway, so you have this expression now of the equivariant K theory in terms of something that has a priori nothing to do with K theory. It really just looks like a homomorphism scheme that's born out of this algebra geometric object. And in fact, something much more general is true. Oh, I wrote it down here. So in fact, spec of H-equivariant K theory, or the categorical fixed points, the genuine fixed points of H-equivariant K theory, is actually always a group scheme in this sense. And in fact, this identification is not just something that occurs on pi 0, it's an identification that occurs as spectral schemes. So as schemes where you're not just looking at locally ringed spaces, but you're looking at locally spectrally ringed spaces. So a higher categorical version of this. So this sort of expression here maybe tempts you to think that a lot of the H-equivariant, a lot of statements about equivariant K theory maybe can be phrased in terms of the algebraic geometry of Gm. And this is just exactly the sort of motivation for tempered cohomology theories. So first, I'm gonna recall a sort of generalization of this Hom stack, or the correct sort of axiomatization, and then we'll see how that fits into this global cohomology setup. Okay, so this is just a recollection of some definitions from elliptic cohomology 3. So a P-divisible group it's essentially axiomatizing what this right-hand side is in the variable H. So it is a functor from the category of finite abelian groups to stacks. I'm thinking of spectral stacks here. If you don't like that, just think of schemes. You could even think of the affine situation. So just think of E infinity rings op. that'll give you a lot of your favorite examples, but I'm going to continue to write stack. So a p-divisible group is such a functor which, and then it has to satisfy these two conditions. So it has to send bicartesian squares to pullbacks and injections of finite groups to finite flat morphisms. The second condition is just giving us some control over the geometry. We don't want these functors to be too random or too big, let's say. And this first condition is allowing us to say something like a product of abelian groups goes to a pullback of schemes, and an exact sequence of abelian groups goes to sort of a predictable fiber square of schemes too. So this allows for lots of reduction arguments. Okay, and is obviously true for this Hom object. So that's what a p-divisible group is. A pre-orientation of a p-divisible group is you take your original p-divisible group and you ask for a factorization like this through the global indexing category, where the map from abelian groups to the global indexing category sends H to the classifying space of its Pontryagin dual. Let me not say too much more to justify this. There's a great discussion of it in section 3.5, I think, of elliptic cohomology 3. And at the moment, you can just think of it as a pre-orientation is a way of asking you to take a p-divisible group and turn it into something that now only depends on GLO. So to turn it into a pre-orientation is a choice of, well, it's a choice of such factorization that helps turn a p-divisible group into something that starts to look like a global cohomology theory. So we say that pre-orientation is an orientation if you look at the following picture. So here I have my pre-orientation. I can take the global sections of my stack and land in E infinity rings, or if you're already thinking of E infinity rings op here, this is just the identity. Yes. So let me go back. So your pre-orientation is an orientation if you take this composite and you write can't extend along the Oneida embedding of the global indexing category into global spaces. So this produces a functor like this, which by construction sends co-limits to limits. By construction, it preserves limits. And if this global cohomology theory satisfies the Atiyah-Siegel completion theorem here, then you call this pre-orientation an orientation. So in other words, you've forced the global cohomology theories associated to oriented abelian groups to already have some nice properties. You've forced them to have an Atiyah-Siegel completion theorem. Okay, so maybe I didn't write it in my notes, but I'll include it here as an example. Starting with the multiplicative group scheme over Ku, you end up with some global cohomology theory, which I like to write like this, which turns out to be equivalent to G-equivariant global Ku. So actually, I don't like that notation. Let me put an underline. So this global cohomology theory associated to this algebra geometric data, should be Ku there, gives us this equivariant cohomology theory, or this classical cohomology theory of Atiyah-Siegel. Okay, so let me stop here for a moment and ask if there are any questions. It's just so easy for me to go so fast if I've pre-written notes as well, I want to give you a lot of information, but don't want to be waterboarded. Okay, so let me just recap. If you have an oriented p-divisible group, in fact, even if it's pre-oriented, you can always define an associated global cohomology theory. And Lurie does a lot with these global cohomology theories in elliptic 3. One of the crowning achievements of that paper is what's called tempered ambidexterity, which is something that I'll get back to later. But one thing that he doesn't do in that paper is he doesn't really explore these global cohomology theories outside as equivariant spectra. He only really studies them as limit preserving functors like this. So one of the main theorems of the recent paper with Sill and William is to refine this global cohomology theory to a global spectrum. In other words, to get that sort of functoriality in transfers, to show that there are coherent transfers there. I have in the corner here, this has also been done recently by David Gepner, Sil Linskens, and Luca Pohl in a paper called Genuine Global Two Rings or something like this, where they also turn tempered cohomology theories into global spectra using related methods. But let me just leave that on the side for now. Okay, so now I can start stating some of.
I have a question, Jack. So because you mentioned this work of Gepna and Luca and so I
Yep.
mean, can one say anything about how many different ways one can have of treating these guys as equivalent spectra?
Yeah, I mean, one of our original plans was to show that there exists a unique lift somehow, and then that would force whatever construction we had to be the same as the Gepner-Linsken's pole construction, but we couldn't quite get it in the end. So there's no sort of uniqueness statement that I think we can make. And it's also it would be very hard to compare our two constructions because although there's a lot of technical similarities, I mean, actually sitting down and writing a comparison seems hard. Yeah, this is
But
yeah, this is a little unfortunate. I mean, they're both constructed using the same sort of thing, which is using tempered ambidexterity as a key result and using the categorification through tempered local systems, and it all somehow. I think you could prove things like if you had a particular transfer that you got from either our paper or Gepner-Linsken's poll, I think you could trace back through the definitions and see that it comes from a certain agreement between a right adjoint and a left adjoint, which comes from tempered ambidexterity. And I think you could say things like, you could say lots of non-coherent things like compare different parts of these global cohomology theories, but comparing the whole thing is definitely something I would ask Sill before I say something bold.
yeah.
Yeah, good question. Thank you. Okay, so this leads me to this leads me to the main theorems. Okay, and well on time too. So this is one of the main theorems of the paper, and it essentially states exactly what I said above. So it says that you can take Jacob's tempered cohomology theory as a global cohomology theory, and you can refine it not just to a global spectrum or a global E-infinity ring, but actually to a pi ambidextrous global E-infinity ring. That's maybe one thing I should say that's a difference between the work here and the Gepner-Linsken's pole is that they only get global spectra, whereas we get these pi ambidextrous global spectra. Excuse me. I should also mention their paper also does elliptic cohomology for compact Lie groups, which we don't touch. So there are advantages and disadvantages. Okay. Yes. So the statement of this theorem is just that there is not just a refinement of this global cohomology theory to a pi ambidextrous global spectrum, but it is also functorial. And the functoriality can be encoded by this sort of diagram. So let me write M for the base stack. So my P-divisible group was a functor from global spaces to stacks, my oriented P-divisible group, and from the global indexing category. And in particular, the global indexing category has a zero object. And if I look at the image of that zero object, that gives me the base stack for this P-divisible group, which I'm just going to write as M. And then you can consider this diagram. So on the bottom here, I just have the global sections functor. So it sends a stack over M, so some X, just to its global sections where X is somehow changed to N. And you can consider this forgetful map from E infinity objects in pi ambidextrous global spectra down to just E infinity rings, which just evaluates your pi ambidextrous global E infinity ring on the zero object, on the terminal object of the category of global spaces. And the functoriality of this assignment can be encoded in the fact that there is a lift like this. So there is a way of sending so the assignment that sends a stack over M to this pi ambidextrous global infinity ring is functorial in stacks over M. So in particular, notice that there is a fixed p-divisible group here. So this G that keeps showing up, it's the same G. So there is a fixed p-divisible group, and I'm looking at different stacks that live over the base of this p-divisible group. Okay, so that's our first statement, is that there is a very functorial way of turning this global cohomology theory into a pi ambidextrous global E infinity ring. And I should say down the bottom here that this is also building on work of Ben Moshe. So also building on work of Shai. And yes, so this is our first statement. So let's sort of unpack what exactly this can give us. So in particular, this you can apply this to the KO situation. So above, I said that if you take the multiplicative group scheme over KU, you get KU as a global cohomology theory. Now I'm saying that if you take GM over KU, you obtain not just a global cohomology theory, but you obtain an E infinity object in pi ambidextrous global spectra. So this is not just a multiplicative global cohomology theory. It also has a whole bunch of transfers, and it gives us these transfers in a very coherent way, which satisfy all sorts of Frobenius reciprocity and stuff like this. And it gives us all transfers for against all pi finite morphisms of global spaces. So that is a lot more structure than what was than equivariant K theory was previously known to have. Okay, so this is fantastic. This is already a good step. Another example that I also usually like to include, which I'll try to squeeze in the bottom here, is if you consider the multiplicative group scheme not over spec of KU, excuse me. Oh, not over spec of KU, but if you take the quotient of spec of KU by the complex conjugation action, so by the usual C2 action that spits out KO, this spits out a pi ambidextrous HO, which is also very nice to have around. Okay, so well, what I've written here summarizes what I'm about to say. So the above theorem captures the functoriality of this refinement of the global cohomology theory to a pi ambidextrous global E infinity ring in morphisms of stacks. But what about if you vary the p-divisible group? So what if you consider morphisms between, well, they have to be morphisms between oriented p-divisible groups because you want them to preserve the pre-orientations. You want them to preserve the underlying global cohomology theory structures. So how can we talk about the functoriality of this assignment now in morphisms of p-divisible groups? Well, it turns out that this is very subtle. And it's very subtle for some very classical reasons. So morphisms of p-divisible groups, maybe you don't think about them very often, but you know some already. So for example, a p-divisible group, if you take something like the multiplicative group scheme, this gives rise to a p-divisible group. And you all know lots of endomorphisms of the multiplicative group scheme. You can take like the n-fold multiplication map. And the n-fold multiplication map on the multiplicative group scheme is going to induce a map on the associated global cohomology theory. And it turns out that this n-fold multiplication map induces the nth Adams operation on equivariant K theory. So this is fantastic. For every n, you get a algebra geometrically defined nth Adams operation in a very coherent way, defined on equivariant K theory, but only as a global cohomology theory, because it's a classical theorem, a classical statement that says that Adams operations on equivariant K theory only commute with transfers if your transfers are co-prime to the n defining your Adams operation. So in other words, the Adams operations don't commute with transfers, so you can't expect Adams operations to lift to maps of all global spectra, at least because it's not going to commute with all transfers. So you can't expect a functor from all morphisms of p-divisible groups to global spectra where you allow for all transfers because it would also contradict this fact. And so that's why the following statement has to be made in such a subtle way. It's what leads to the following theorem. So it says that if you choose any set of primes S, then there is a functor which goes from some category of oriented p-divisible groups where morphisms with morphisms boring away from S. So maybe I'll just say out loud what I mean by boring. So by boring, I mean they're morphisms of p-divisible groups such that when you look at a p local component for each p inside your set of primes S, for each p not in your set of primes S, sorry, it's an isomorphism. So this means that for all primes that are not in your set S, this map is an isomorphism, so it's a boring map of p-divisible groups. We're interested in non-isomorphisms. And what is this category over here? This is, so this S perpendicular to pi is some subcategory of this category pi that I talked about before. So these relatively pi finite maps living inside this global, this category of global spaces, where the morphisms are, again, co-prime to S, where morphisms are sufficiently co-prime to S. And so the statement of this theorem is essentially saying that the assignment that I talked about in the previous theorem that sends an oriented p-divisible group to the associated global ambidextrous cohomology theory, it refines to a functor from the whole category of p-divisible groups with morphisms that are boring away from S, as long as you consider the target category to be some category of global spectra where you throw away all your transfers at S. So let me say that again. The morphisms here are interesting at S, whereas the transfers, there are no transfers here at S. So you're exactly avoiding this problem that I mentioned with Adams operations. You don't have an nth Adams operation in Cn equivariant Ku because it doesn't commute with these sorts of transfers. But if we throw away this problem, it turns out that we do have a functor defined like this. And so keep in mind, if the category of primes is very, I always need to think about this for a moment. If the category of primes is very, very big, then we don't have many transfers, but we allow for lots of morphisms of p-divisible groups. So we have lots of morphisms of p-divisible groups, but we don't get many transfers on the other side. Whereas on the other hand, if your set of primes is very small, then you're only allowing for a few p-divisible groups, but these morphisms of p-divisible groups induce morphisms on the associated tempered cohomology theories, which commute with a lot of transfers. So in particular, if you take your set of primes to be empty, you recover exactly the previous theorem, because then you only have isomorphisms between p-divisible groups. And conversely, if you take your set of primes to be all primes, you have the statement that says that a statement that's essentially an elliptic cohomology 3 that says that all morphisms of p-divisible groups induce maps that commute with no transfers. Okay, that statement I just said is rather empty, but I'm trying to illustrate the sort of balance on choosing your set of primes S here. Okay, so I only have about 10 minutes left, and I would like to get to some applications, but I would also like to give you a bit of okay, I wanted to consider another example here, but I think I'm going to skip it, which pains me to do so because it is the TMF example. So I'll just say that out loud. So if you take the moduli stack of oriented elliptic curves, then that has a universal elliptic curve living over it. You can apply this technology, and you end up with a tempered cohomology theory, which refines to a pi ambidextrous global spectrum, which gives us some sort of pi ambidextrous TMF. And this is really lovely. This is one reason why I was very excited about this project. Okay, so rather than talk more about examples, let me talk briefly about the proof, and then I want to talk about some applications. So what happens once we know that we have these global equivariant structures on these tempered cohomology theories? What are some things that come out of that? But let me start with just a bit of a proof outline. So we want to construct a functor like this from oriented p-divisible groups into some variant on ambidextrous global spectra. And we're going to do that in two steps. We're first going to categorify the situation by sending a p-divisible group to Lurie's infinity category of tempered local systems on G, which we recognize as not just as a category, but actually as a category parameterized on GLO-AB. Excuse me. So this was already noticed, this fact that tempered local systems were already not just a collection of categories, but actually assemble into a parameterized category was already observed by Shai. And then we just observed that Lurie's tempered cohomology theories, Lurie's tempered ambidexterity theorem allows you to refine this not just to an E infinity object in GLO parameterized categories or a symmetric monoidal GLO category, but also to add some sort of parameterized stability and parameterized presentability. So in other words, the tempered ambidexterity theorem is an equivalence between a left adjoint and a right adjoint of a restriction map. And this agreement between the left adjoint and the right adjoint is what gives certain Beck-Chavalet conditions, which is what gives us this parameterized presentability. And that is what in the end gives us these extra transfers. So the fact that the tempered ambidexterity identifies two maps, and then you have this category theory that says, once you have adjoints that agree, blah, 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 you get a bunch of transfers in a very natural way. That is how the sort of transfers are born from this situation. So that's what we call theorem C in the paper, and that's what we spend most of section 4 working on. And but then we need a process to come from our categorical situation back down to some variant of global spectra, and that's where we need to do some decategorification. So we need to send our symmetric monoidal Q-presentable GLO category, we need to send it to the associated ambidextrous global spectrum given by endomorphisms of the unit of our category. let me forget all of the parameterized adjectives for a moment. This is just a parameterized version of the fact that if you have a symmetric monoidal stable infinity category, let's say it's presentable as well for fun, then the endomorphism spectrum of the unit of that category has a canonical E infinity structure. And there is a functor like this, and this is just the parameterized version of this. But setting all of this up takes a lot of time in this paper too. Okay, so that's roughly how the proof goes. I'd love to give more information, but yeah, then it would turn into more of a lecture course. Okay, so in the last few minutes, then let me just talk about some of the applications. So I'll be a little bit quick with this. So we have all of these nice theories. So what are we going to do with them? Well, the first thing we do is that we recognize that if you fix, so you have all of these pi ambidextrous E infinity rings, so you can evaluate them on things like BH. And if you evaluate them all on BH, you end up with a sheaf on your base stack M, a sheaf that looks exactly like this. And one of our first observations is that you don't actually just get a sheaf, you get a quasi-coherent sheaf. And associated to every quasi-coherent sheaf, or an algebra object in quasi-coherent sheaves, is a relative scheme or a relative spectrum. So this is how, so we turn these ambidextrous objects, these pi ambidextrous global infinity rings, back into algebraic geometry pretty quickly. And the nice thing about this is that you can do it for any finite group. It doesn't necessarily have to be abelian. Before we had a definition of this when this was abelian, but now this applies in the non-abelian case too, which is very nice. So this gives us a nice geometric object to play with. And then we define what we would call tempered homology. So what you do is it ends up being some sort of collection of notation like this, which is a functor from H spaces to this category of quasi-coherent sheaves on this geometrification of the values of the pi ambidextrous global E infinity ring on BH. And this H-tempered homology theory is roughly speaking defined as follows. I mean, it's colimit preserving, so I need to tell you what it does on the generators of H spaces. And what it does on these generators, like these orbits, is it just sends it to the value at BK of this global cohomology theory, of this sheaf, sorry. And the functoriality now, it's the dual functoriality from what we started with. So we started with a cohomology theory, which was giving us contravariant functoriality, but then we also had the transfer maps, which is exactly what we're using here to get to build this tempered homology. So you use these transfer maps here to construct these homology theories. So we also construct global homology theories too, and it's very convenient that we worked in this expanded setting where we allowed for a lot more transfers, because that allows us to construct a lot more refined homology theories, because we're allowing for a lot more morphisms coming from these transfers that we've allowed. Okay. And these tempered homology theories, sorry, they come with very powerful base change theorems in a very similar vein that the universal coefficient theorem, or no, I shouldn't say that, the Kuhne theorem for homology looks a lot nicer than the Kuhne theorem for cohomology, because for cohomology, you need to make some finiteness assumption on the spaces involved, whereas for homology, you don't. And so this is sort of a global coherent version of this, this sort of base change theorems. So for example, if you open up elliptic 3, you'll see a collection of base change theorems for tempered cohomology, and they'll all have some finiteness constraints. But using this definition of tempered homology, you can throw these finiteness constraints away. Okay. Yes, I mean, I've been talking about these. One thing you should notice is that these tempered homology theories take values in quasi-coherent sheaves, and maybe you don't like that. Maybe you're like me when I first started seeing these things, and I was maybe a bit apprehensive about the algebraic geometry. And you sort of tried to go from the algebra geometric picture back to the algebraic picture, to the higher algebraic picture as soon as possible. So maybe you want to take this quasi-coherent sheaves category and you want to take global sections so that you can land in the category of spectra. And you can do that. So you can always apply global sections and you will always get a reasonable homology theory in spectra, as long as this global sections functor commutes with colimits. Because of course you want your homology theory to commute with colimits, and since you're defining it as this composition, then you also want your global sections to commute with colimits. And but this is true in a lot of generality. So this is true in lots of cases. So in lots of cases, you don't have to stay in this global setting, in this geometric setting. You can go to the sort of affine setting. So the previous paper of Sil and William and mine is on zero affineness, sort of building on the work of Matthew Meyer, where one of the key things they study is when is the global sections functor co-continuous. And there are lots of examples of that. For example, the moduli of oriented elliptic curves, or Ku mod C2. Okay, so one thing that you get from these tempered homology theories is you get a notion of geometric fixed points. So, and you get this just really in exactly the same as how you get this classically in H-equivariant homotopy theory. You just look at the homology of a certain universal space with respect to proper subgroups. And so yes, so we can define, you can take this spectrum, you take this sheaf, this quasi-coherent sheaf, you can apply the relative spectrum, and you get a geometric object which represents the geometric fixed points of this P-divisible group. So I know it's 6 o'clock now, so let me just quickly say the next theorem quickly. So the last thing that I wanted to talk about today was how one can use this construction of the geometric fixed points of tempered cohomology theories, and how one can actually study them very well. So we have the following theorem, which says that if you try to compute these geometric fixed points for non-abelian groups, then you always get 0. So of course I say 0 because I'm thinking of the algebraic situation. In the geometric situation, you say that the geometric fixed points, or that this scheme is empty. So this is very similar to the situation for K theory, or something like this. If you take its geometric fixed points, they're really concentrated at abelian groups, in fact, even at cyclic groups. And in fact, this is a general thing for these types of tempered cohomology theories. It's in the language of Matthew Nama Noel, it's saying that the derived defect base of tempered cohomology theories is always contained in the category of finite abelian groups. And we also do something in the abelian case. We say that, well, if your H happens to be abelian, then there is a moduli description of this geometric fixed points as some stack of injections. And so what do I mean by this stack of injections? Well, you take a stack of homomorphisms and you cut out all of the homomorphisms which come from proper subgroups. So this is what we essentially define as the category of injections. And we give it, the stack of injections, and we give it such a name because of coming from this intuition. So the thing that I want to end on is that this geometric model for the geometric fixed points is also very, very useful to work with. So for example, using this geometric model, you can prove a sort of blue shift for geometric fixed points. So you can prove that, you can prove some sort of blue shift. So if your P-divisible group has height h, then the chromatic height of this stack, this H geometric fixed point scheme, is always bounded by the original height of your P-divisible group minus the what do people call that? The P rank of the abelian group H. So this is very useful in studying these geometric fixed points. It really helps in at least in all the examples I know, it really plays a key role in trying to make computations. I have a few other examples using this geometric model for the geometric fixed points, but let me just finish there, and thank you all for listening.
Thank you very much, Jack. Let's all give the speaker a round of applause.
Thank you. Thank you.
Any questions, anyone?
Hi, yeah. Can I ask about how does the multiplicative structure of this resulting spectra work with this? Or so if you take, for example, yeah, KU, do you see a compatibility there or?
Which infinity structure are you talking about?
So, I mean, you mentioned that you endow KU with a structure of an infinity object in this category of pi ambidextrous global spectra. I assume that this here by infinity, you mean that you are not discussing the norms at all. This is just an infinity object here.
That's a great question. Yeah. It's really naive infinity in the.
Yeah, and there's no way to obtain any sort of compatibility between these two structures that you know of. Or...
You mean between the norms and what's happening here?
Yes.
No, that is forthcoming work. So in forthcoming work, we sort of with Sil and William, we talk about the compatibility for KO and KU and TMF. But I think the question of where do the norms come from using tempered cohomology and using the algebra geometric language is complicated. There's already a shadow of this in the literature if you look at like the Ando Hopkins Strickland paper on the theorem of the cube, or the BU6 the sigma orientation of TMF. They're already talking there about like, okay, you have some sort of extra multiplicative structures on your elliptic cohomology theories, but only if your schemes, your algebra geometric objects are endowed with extra structure, like descent with respect to subgroups. And this is
okay.
You need a lot more. I'd love to talk more about it. We can maybe talk some other time.
Nice, thank you. Yeah.
All right now. Okay. Any other questions? So Jack, I mean, you mentioned this briefly towards the end that you get some of these computations of the derived effect base. And I also remember seeing in your preprint that you got back, I don't know if you mentioned TMF now or if it is mentioned in the paper. So one advertisement, it seems to me, of this theory is this application that you can compute derived effect bases quite explicitly in some cases. Would that be a correct thing to say?
Absolutely. So for the only epsilon that you need to worry about is, of course, computing the derived defect base is doing two things. It's putting an upper bound on, like, it's computing exactly the support of your geometric fixed points. So this sort of theory, like, where is it? Yes. So is that what I want to say? Yeah. So using this sort of expression here can really help you put an upper bound on that. Like, it definitely says that, okay, they're contained in finite abelian groups. And if you stare at this chromatic blue shift, you can also see that they're, like, if your P-divisible group has height H, then the derived defect base is contained within finite abelian groups with at most H generators, which is how we get like the derived defect base for TMF being such guys with at most 2 generators. And it also recovers the classical statement for K-theory that, of course, the geometric fixed points of K-theory are only non-zero for cyclic groups. Yes, it only gives you an upper bound. So, of course, there's then checking a lower bound, but that can usually be computed using the base change theorem. So I mentioned this base change theorem, which holds for tempered homology. Since it holds for homology, it holds for geometric fixed points. So then you can base change from, like, whatever base you're working over to, like, let's say a field or Lubin-Tate theory or something like this, where you can do character theory or something like this. Yeah.
So I was wondering, like, usually, I mean, I could be completely wrong here. Usually, when one tries to prove things like Achilles thick subcategory theorems, I mean, of course, I think that was done before the MNN paper. So one would make good use of the computations of the derivative defect base that you are coming up with, maybe also to prove, like, essentially stratification results. Is that,
Huh.
does this make sense?
That does make some sense, but I should sit down and think more about like so you're sort of referring to some sort of stratification of like the Balmer spectrum of
Yeah,
like
yeah,
mod KU in
yeah.
U spectra or something.
I think Akhil did it for famously for TMF first, and it was quite a 2015 or yeah.
Yeah, so for 2015 he did this and it was very he was sort of using the zero affineness and a lot of and some extra hard work. He sort of showed it was the
Yes,
same as the closed subsets of it sort of looked just like the moduli of elliptic curves.
yes,
Um,
exactly. Yeah.
yeah, and I guess yeah, I mean there's one has a lot of control over these sorts of algebra geometric objects here as well. I mean, one could probably that's a good question. I think this sort of stuff would definitely be helpful if one wanted to try to explore like the Balmer spectrum of these tempered theories or something.
Okay.
Um, for one thing that I've been doing a lot recently together with Luca Paul, for example, is like thinking about Picard groups of these things because
Right.
you know you can use lots of Tate square decompositions to
Okay.
decompose your tempered cohomology theories into their geometric fixed points with Weyl actions, and then you can just try to use these sorts of models to compute things. It's quite approachable, I think.
I think I saw some techniques like exactly what you mentioned now in that Hopkins Picard groups referenced by Toby and Tomer and
Yep, and
Jared Weinstein.
yeah, Jared, and I think Nat was in there too. Yeah,
It was it. Yeah, that's right. Yeah.
yeah, definitely. Um, yeah, I Yeah, I mean, one other thing, and this is something that I've been talking to Luca a lot about and thinking a lot about myself, is that there's this paper on equivariant separability in equivariant algebra with Nico Naumann and Luca Paul and Maxim Ramsey, and in it they use a lot of decompositions of equivariant module categories using geometric fixed points with Weyl actions and stuff like this. And these sorts of models for the geometric fixed points are really helping understand this picture. And in fact, and this was something that this is something that have been working on myself. It'll hopefully be done soon. Is that you can even study the residual Weyl action on these geometric fixed points using this algebra geometric perspective because you can interpret that in terms of some sort of action on this inch stack. And then you can study sort of, okay, if I have an action on this inch stack, is it locally free? Is it a torsor? Is the associated action on the left-hand side actually Galois? You know, is that going to help with computations? Yeah, there's a lot that could be said. I'm very interested in this stuff, hence my very long
No,
rambling
no, no. Yeah.
answer.
Great. Um, does anyone else have any questions? If not, let's thank Jack once again.
Yes, thank you for the invitation. Thank you all for being here too.
We will have a stability conditions talk next week, and that's not homological stability, that's Bridgeland stability. The next topology talk will be by Ishan on the 28th. Yeah, hope to see you there.
Okay, hope to see you there.